Now we'll start looking in more detail about how to calculate the moment of inertia for cross-sections that are more complicated than just a simple rectangle or triangle. So we go back to the same list, the same reference that we used when looking at centroids, and there's also information here about how the moment of inertia is calculated. So the first step usually is we need to find the centroid of our shape, or as we're going to see for composite shapes, each of the subshapes. Then we have a calculation here for what is its moment of inertia about the horizontal centroidal axis and the vertical centroidal axis. So again, those are the axes that pass through the centroid of our shape. So we'll start here looking at the quarter circle. We see that its resistance to bending about the horizontal centroidal axis, that is what I sub x is. So 1/16 pi r to the fourth. And then about the vertical axis that passes through the centroid, that's I sub y, that's also 1/16 pi r to the fourth. So again, notice the units we're going to have. We have this radius to the fourth, we have a length to the fourth in our calculation. Going to the semicircle, we have its I sub x, I sub y. Both of those here are 1/8 pi r to the fourth. For the full circle, its centroidal axis passes through the center for the vertical and the horizontal. So both of those measures are this I sub x and I sub y, 1/4 pi r to the fourth are going to be those moments of inertia. Now, most commonly in this course, we are going to be seeing rectangles and triangles most likely. So we know how to find the centroid of a rectangle is just half of its height, half of its base. So around the horizontal axis, we are going to have here, again, they say 1/12 bh cubed, and then around the vertical axis, 1/12 hb cubed. The best thing to remember for this is that the dimension that is perpendicular to the bending axis gets cubed. The dimension parallel to the bending axis is to the first power. And that will be less confusing about which is the base, which is the height. Cube the dimension perpendicular to the bending axis. And finally, for triangular shapes, its calculation is 1/36 bh cubed. Again, the dimension perpendicular gets cubed. The dimension parallel to the bending axis is to the first power. Now, all of these basic calculations, again, usually we'll be dealing with rectangles for the most part. The 1/12 bh cubed is for a rectangle, its moment of inertia about the centroidal axis for its own shape. But when we are dealing with composite shapes that might be made up of multiple rectangles, we're going to have to go a little bit further because we are going to want for the composite shape its resistance to bending, its moment of inertia about its centroid. So the problem we're going to encounter is that the subshapes are going to have these axes going through their own centroids, but we want to know how does it resist about the centroid of the entire shape, because those axes might be different. So these calculations, the 1/12 bh cubed or the 1/36 bh cubed is a starting point, but we're going to have to make an adjustment because we don't want to know just how does it resist bending about its own centroidal axis, how does it resist it about the centroidal axis of the composite shape. So we're going to need to make a compensation here called the parallel axis theorem. So if we want to know how does a subshape resist bending around the x-axis, the horizontal axis that passes through the centroid of the entire shape, we are looking for what notation-wise I'm going to call I sub xx. But those calculations, the 1/12 bh cubed, that is telling us what I am going to be calling this I sub xx prime. So this is about its own centroidal axis. To find how much it resists about the centroidal axis of the composite shape, we have to add to that measure this ADX squared. And it's going to be the same idea if we're looking at the moment of inertia about that vertical centroidal axis. We're going to calculate it about its own centroidal axis, own vertical centroidal axis, and make an adjustment, this ADY squared term. So this compensates that we are trying to find its resistance to bending about a parallel axis to the one that passes through our subshape's centroid. Now, how do we do this calculation? This dx I am going to define as the distance between the y-axis passing through the subshapes centroid and the y-axis passing through the composite shapes centroid. So if we look here, it's the difference between y tilde, which we used to find the centroid, and y bar, the location of the centroid for the composite shape. dx is actually a vertical measurement because y tilde is going to be a horizontal axis and y bar is also a horizontal axis. So we just want to be careful with how we're using the notation here. D sub x is going to be the difference between where the y bar axis is located and the y tilde axis is located. Now the order is going to turn out not to matter, so I'm defining it here as just the absolute value. So the dx and the dy, it's fine to always just take the positive value there. As we'll see, it's only ever going to get squared. So for each subshape, we need to make this parallel axis adjustment, and we have to note that each subshape will have its own y tilde. But y bar is the same for everything because that's the axis that passes through the centroid of the composite shape. So we do this for each subshape that we have made, and we can add all of these terms together in order to get the total area moment of inertia about the centroidal axis for the shape. We're going to see that the first step in calculating the area moment of inertia is we need to find the centroid first, because the centroid is going to tell us the x bar and the y bar, and then we're going to be able to make these further calculations that are going to employ those values. So because we're starting with finding the centroid, we can actually expand upon the tabular method that we already looked at in that section when we were looking at the centroids. So we can start with the table that we're already familiar with here. We have already divided our total shape into these subshapes, 1, 2, 3, however many subshapes it took. So let's assume we have already found x bar and y bar. Now we're going to expand on the table that we've been working with. So I'm adding more columns to this table. For each shape, I want ixx prime, iyy prime, this dx calculation, the dy calculation. Then these are just going to be products. I'm going to take the area of the shape times the dx squared and the area of the shape times the dy squared. So for each shape, we need to fill in these columns. The ixx prime, that is the area moment of inertia of the subshape about its own horizontal centroidal axis. Iyy prime, same idea, the subshape's moment of inertia about its own vertical centroidal axis. dx, we've actually already have every ingredient for. dx is going to be the difference between that shape's y tilde and the y bar, which we've already calculated for the composite shape. So dx, we just have to do that difference. dy is going to be the x tilde of the shape minus x bar for the whole shape. So we already have all the ingredients, we just have to do that calculation. And finally, we're going to multiply per subshape its area times its dx squared, and then the area times the dy squared. So this is why the sign on dx and dy doesn't matter. The only thing we really use it for is squaring it and multiplying it by the area. So finally, what we want to do, if we want ixx, that is the total moment of inertia of the composite shape about its own horizontal centroidal axis, we can add up all the I prime xx values in this summation and add to that all of the adx squared values. So that total sum tells us the area moment of inertia about the horizontal centroidal axis. Same idea to calculate Iyy. We take the sum of all the Iyy primes, so the value in this cell, and we add to it the sum of all the ADY squared terms. So we add this cell and this cell together, add them up, and that gives us the total Iyy for the composite shape.